So if the last chapter was mostly about triangles, what we're going to start working on in chapter 6, and a big focus is properties and ways of proving quadrilaterals are parallelograms. So our first note that we have here, a parallelogram, is any quadrilateral that has both pairs of opposite sides that are parallel. So that name comes from. Can abbreviate parallelogram with a symbol, which is basically a drawing of a parallelogram. So that symbol, if I have that kind of parallelogram shape, we can just use that just like we use a triangle symbol or some of your other angle symbols, things like that from earlier. So in a quadrilateral, opposite sides do not share a vertex and opposite angles do not share a side. So we've seen those terms before, but we just want to remember that opposite means, again, they're not touching, sides, and opposite angles, again, same thing, they're on opposite parts of that parallelogram. So first couple properties that we have, and also, again, we have converses too, so if I can flip these rules, is that if a quadrilateral is a parallelogram, then I know that opposite sides will be congruent. So any parallelogram, opposite sides are congruent. So if I start with a parallelogram, I know that AB and CD are the same, and BC and AD will also be congruent. And when I say converse, that just means we can reverse that rule. So if you see that opposite sides in any quadrilateral are congruent, that's enough to prove that we have a parallelogram. So again, converse means I can flip that statement, and it's still true. So angles in a polygon that share a side, we call them consecutive angles. We saw that term before with parallel lines. Consecutive angles, again, will be next to each other basically. So in the diagram, angles A and B are consecutive, B and C are consecutive, C and D are consecutive, and D and A are consecutive. Again, as long as they share a side, those are consecutive angles. So a few more properties we can use now that we've defined that term consecutive is that any parallelogram will have consecutive angles that are supplementary. So for example, if I have my quadrilateral given, then A and B will add up to 180, B and C, C and D, D and A. Any two consecutive angles should be supplementary. And again, it's converse, so that means that if I start with a figure where the consecutive angles are supplementary, that's enough proof to figure out that something is a parallelogram. Other rule here, if a quadrilateral is a parallelogram, then we also know that opposite angles are congruent. So if I start with a parallelogram, that tells me that A and C would be congruent. Those angles are opposite. Also, B and D would be congruent. Those are the other pair of opposite angles. Same thing, it's a converse, so I can also flip that. If I know that A and C are congruent, and also B and D are congruent, that's enough to prove that I have a parallelogram. So trying that with some practice, if we're looking at this figure, I think we do have to assume that this would form a parallelogram if I have this desk lamp and I have the part of the lamp that's extending upwards here. I could know the measure of angle P if I was given the measure of angle S from the diagram, because P and S are consecutive angles in that parallelogram. Since they're consecutive angles, I know that if I take 180 and subtract angle S, that'll find me the measure, so 116 is the measure of angle P. Again, because I know that these two are consecutive in a parallelogram, those should add up to 180 because they're supplementary. Same idea for the next question. If I adjust the lamp so that angle S is 86 degrees, angle R is just the other supplementary consecutive angle. So if those are still consecutive, I can still just take 180, subtract angle S, and that tells me that angle R would be 94. That's for the same reason from before, I know that those consecutive angles should be supplementary. Looking on to some more practice, if I want to figure X and Y to figure out if I have a parallelogram, I guess just Y in this one, we actually have to start first by solving for X. If I just use the fact that PS and QR are the same length, that's true, but I also need to use the fact that these opposite sides are congruent. So if 3x minus 5 is equal to 2x plus 1, I need to solve that first because I need to figure out what x is and use that to plug in. So if I set that up so that the top is equal to the bottom, I can solve and get that x is 6. And then if I substitute 6 plus 2, that tells me that y is going to be 8. So same kind of idea here, although we're using a different property. You could use opposite angles, so you could set up a system of equations to solve this, but I think the easier equation to use, rather than using the opposite angles, is use the consecutive angles. If I know that angles E and angle H are consecutive, that means that 3y minus 2 plus y plus 10 should add up to 180 because those consecutive angles are supplementary. So all we got to do is combine like terms, subtract, and divide to solve for y, get our answer for y. And for x, we're using the same rules. So if I have f and g that are consecutive, that means those will be supplementary. So same thing, I combine like terms, subtract, and then divide to find my answer for x. So next property that we have for our parallelograms is that if I have a parallelogram, that means that the diagonals will bisect each other. So we saw that bisecting before. Remember, that means that it's cutting each other in half. So if I cut those diagonals in half, that means that the first half of this diagonal from A to E, that will be congruent from C to E. And also for our other diagonal, BE will be congruent to DE. So when I have diagonals in a parallelogram, that means I'll be cutting those into 2 equal pieces. Since it's a converse, again, that just means that I could reverse that rule. So if I see that the diagonals are bisected, if AE and CE are congruent, and also if BE and DE are congruent, that's enough proof to show that I have a parallelogram. So let's try and use that with some algebra as well. If I want to solve the system of linear equations to find x and y, what that means in this question is that I know the diagonals are being bisected. So we can't say, for example, that 2x minus 8 is equal to x. I can't use an equation with those because I want to be using the same diagonal for each question. Since I know km is being bisected, I know that y plus 10 is equal to 2x minus 8. And since ln is also being bisected, I know that x will be equal to y plus 2. So after I have that system down, I think the easiest method to solve here is substitution. Since x has already been isolated, I can take my expression for x and substitute that in my other equation. So if I then have y plus 10 equals, and instead of 2x, I have 2 times the quantity y plus 2. Again, I substituted that instead of x. That's minus 8. Again, I just wanted to make sure we can solve this and isolate for y. So I distributed. Looks like next step is I combine like terms, and then if I move the y around, so if I subtract y on both sides and add 4, I end up getting that y is 14. And if I want to find x, since I already know what y is, I can plug in, looks like my second equation is going to be the easiest. X is just y plus 2, so if x is 14 plus 2, that makes x 16. If I want to find km, I could plug into both of those. So what I did in my work was I plugged in my answer for x and I plugged in my answer for y, because if I add those 2 segments together, that would be the length of km. So plugging in for both, we could find that each one is 24, and we could find that way km put together is 48. Another way to do this, though, is if I'm just looking for the entire length, so this time if I'm looking at ln, for example, you don't have to plug in for x and for y. A little bit of a shortcut here is that we know that those halves are both the same. So ln would be the same as basically just x and x put together. So that way we can just plug in a little bit quicker. If x is 16, 2 x's will be 32. And again, that equation is a little bit different because if I take x for the first half, instead of y plus 2, I can also assume it would also just be x for the second half. So 2x is a little bit easier to solve than plugging in for both variables. We do have another practice question that's like that, so let's try that again. If my diagonals are bisected, that means 2 things. It means y is going to be equal to x plus 1, so breaking up this diagonal evenly, and also the other diagonal, 2x, will be equal to 3y minus 7. So I think another time this is going to be substitution. So substitution, I have the y isolated. I want to use that expression, x plus 1, to plug in my second equation. So if 2x is 3y minus 7, instead of the y, I'm going to replace that with x plus 1. Got that from the first equation. So same steps as before. Distribute, combine like terms, subtract 3x, it looks like, on both sides, and we end up getting that x is going to be 4. After I know my answer for after I know my answer for x, I'm going to take that and plug that back in so I can find y. So 4 plus 1 gives me 5 for y. And same thing with the last step here is you can take a little bit of a shortcut. If we want to get PR, looks like my simplest expression there is just 2x. So if I have 2x for one half, that means I'll have 2x for the other half. Easiest thing I think to plug in there for is just plugging in as 4 times x. So if PR is 4x, and we know that x is 4, I get that PR is 16. So same thing for SQ. If I know that SQ is these 2 parts put together, you could plug in for both. It wouldn't be that tough here, but if we also know that y is 1 half, that means y will be the other half. So if SQ is 2y, 2 times 5 will give us 10 for that total. You could also find 1 half and then just double it. So if I found that y was 5, if I double that, I get 10. So same thing, if I find that this half was 8, if I double this, I get 16. So we're working on a proof for the next one using some of those new properties. And this we're given two things. The fact that we have a parallelogram, ABCD, and we also know AK and MK, those two segments would be the same. So we want to make sure we list the given first. Again, we can use that parallelogram symbol to refer to that first given. My first step, and again, steps 2 and 3, you could pretty much interchange in any order. I said first that angle BAD in this bottom left corner would be congruent to angle BCD, because since I know this is a parallelogram, one of the properties of parallelograms is that opposite angles are congruent. So the way that I listed that reason is pretty much stating that anytime we start with a parallelogram, that means that opposite angles are congruent, so I know that those two are the same. A little bit separate reasoning for step 3, that's using part of the given. If I know that AK and MK are the same, what that does is makes this a big isosceles triangle. So since it's isosceles, angle BAD in this bottom left corner should be congruent to the other bottom corner, so CMD, because if I have congruent legs for AK and MK, that means my two base angles will be the same. So BAD, this in the bottom left, and this angle CMD in the bottom right, those will be congruent. So again, same kind of reasoning. Congruent legs means I'll have congruent base angles for my triangle. And now that I have steps 2 and 3, it looks like BAD is congruent to two different angles. So since BCD and CMD are both congruent to the same thing, that means they're congruent to each other. And again, we call that transitive property. So POC I just added in there at the end just to state that that's a property of congruence, but the important part there is that we know transitive links together two statements using the fact that BAD is congruent to both. So one more way to prove that we have a parallelogram that we're adding in, if we know that one pair of opposite sides are both congruent and parallel, that would be also another way to prove that we have a parallelogram. And it does have a converse too, so the converse would also be saying the same thing. If it's a parallelogram, I'll have a pair of sides that are congruent and parallel. So again, that means that I need both for one pair of sides. I need the fact that they're congruent and also the fact that they're parallel. So you should see both of those markings if it is marked in a figure that way. So we're going to try and use those facts and any of those other properties we've seen before to see if we can prove that we have a parallelogram. In that first example, it looks like we have a 50 and a 130 degree angle. We also have a 5 and a 5. So since I know that these two, the 30 and the 130 and the 50, if those are supplementary, that means that AB and CD, should not be marking those congruent, should be marking those parallel. So I know they're parallel because the same side interior angles are congruent. That's going all the way back to parallel line properties. I have same side interior angles, those are congruent, they're supplementary, so that tells me that these two lines are parallel. And we also know that since AB is 5 and CD is 5, those are congruent. So that's using our last property that we've just seen. Since AB is congruent to CD, and since it's also parallel to CD, I have one pair of sides that is one pair of opposite sides that are congruent and parallel, so that does make a parallelogram. Our next situation looks like I have two sides marked congruent, two different pairs of sides marked congruent, but this would not be a parallelogram because the sides that are congruent are not opposite of each other. So for it to be a parallelogram, I would need KH to be congruent to IJ and HI to be congruent to KJ, but we have those pieces flipped around a little bit. So last page, basically one last topic we want to see. If I have 3 or more parallel lines that are cut off by congruent segments on one side, that means that the congruent segments will be cut off on every transversal. So on the left, if I know that AC and CE are congruent, that tells me on the right that BD and DF will also be congruent. So just using that really quickly for one practice, and I'll leave that lesson summary to see if you can fill that in. If I know that AB, BC, and CD are all 2 in this figure, and if I start off with the fact that EF is 2.25, that tells me since they were cut by parallel lines, the other two segments that weren't given here were both 2.25. So if I'm looking for EH, add all those 3 together or just multiply by 3 and we get 6.75. So again, I'm going to leave that lesson summary. I'm going to list an example of what that should look like. So you're just trying to list those properties that we know of parallelograms. The more that you can remember, the more this is, the easier this is going to be as we start adding in these rules, do things like proofs and solve some questions.